Let's see how much we manage to do. Yeah, okay, so since we cannot touch the blackboards and there cannot be a recording in the other room, we decided we are going to try to do this like this. So I just forgot, I wanted to get my bottle of water, 1 second. This is part of the lecture. Yeah, so we are starting back where we got yesterday. Namely, we were looking at this example. If this is visible enough. So we were looking at this example where we call the bubble, and we said this integral family, I was calling the integrals I, A, and B, where these are the powers of the two propagators. And we said that this integral family has two master integrals. One was the tadpole, and the other one was the bubble, right? Corresponding to these two guys here. And then I derived a set of differential equations, in particular one differential equation, a system of differential equations for the two. The derivative in, say, the momentum that they depend on, so the p squared. And it looked like this. So I think after a rotation, we wrote it finally in this nice form. Let me try to write it out explicitly. There was an epsilon factorized, and then we had 0, 0, 2 over square root p squared minus 4m squared. Can you read? Is it readable? And then p squared minus 4m squared, and then the two integrals again. And remember that to get to this form, where I always use this epsilon is, in this case, it's actually 2 minus d divided by 2. Right? Because we said we are studying the problem close to 2 dimensions instead of 4 dimensions, right? And I told you, that to get here, practically I started from this original basis, and then I rotated away what I call the maximal cut of the two diagrams, which corresponded really to the solution of the homogeneous equation, okay? And we kind of said this is a little bit of a magic thing that happens, right? Because there is this epsilon factorized, and then there are these differential forms here that appear in the matrix. I mean, I can imagine of writing really this equation in differential form, something like that. If the problem depends on many variables, I can write it in general in this differential form, where this is the what is called the Gauss-Manin, or if you want, the matrix of differentials. This is my basis of integrals, and this is the differential of the integrals, and this is epsilon. And this here, this basis here is independent. Sorry, this matrix here is independent of epsilon. And we said that something in this form, in particular when the singularities of the differential forms, like here, are logarithmic. In this case, we said these are explicit T-logs, are really differentials of logarithms. It's what we call a canonical basis. Okay, this is where we had gotten yesterday. Now, I would like to say two things. So there was a question actually from some of you. What happens? I mean, could I done exactly the very same thing, say in 4 dimensions instead of 2 dimensions? This is the first thing. And the second question is actually, what does the solution to these things look like? Okay, so I would like to start maybe from the second question, because it's easy. We have already the equation. Let's try to solve it. Okay. Now to solve it, I'm going to do something very similar to what we did when we tried to integrate the Feynman integral in Feynman parameters. Namely, I'm going to introduce what is called, again, the Landau variable, but this is just a change of variable which rationalizes, actually linearizes in this case, the variety represented by that square root over there. So this Landau variable is the following, is a nice definition. It's just the mass itself, and then we put actually a minus sign here, 1 minus x squared over x. So I'm going to go practically from p to x. The rationalization, if you want, is a rational parameterization of this algebraic variety. It's practically a square root of degree 2. It can be rationalized and is equivalent to a sphere, right? This is what we know from geometry. And so this is a special rationalization which is particularly nice for physics, because when p squared takes like values that are, if you want, of physical relevance, then x goes typically from 0 to 1. Okay, that's why this parameterization is particularly nice. It doesn't matter too much. What matters is that in this new variable x, let me try to write it here, the equations look like this. So there is derivative with respect to x, j1, j2, and then I have epsilon, equal epsilon, and then again 0, 0, and then minus 2 over x, and then 1 over x minus 2, 1 plus x, j1, j2. So if I go to this parameterization, you see immediately that these are d logs, right? Are differentials of logarithms. This is a log of x, and this, of course, is a log of 1 plus x, and the log of x. There is only one variable, and everything is completely manifest. Solving this equation also in this form is completely straightforward. It also tells you, right, that the solution, you see that the very nice thing is that if the differential equations take this form, then my solution, if you want the vector j, can really be written as a path-ordered exponential. If you want to be really precise, you can imagine of writing it like this, over this matrix of differential forms times whatever is your boundary condition, right? So I can write it somehow in closed form like this, and since I'm at the end of the day, I'm interested in expanding in epsilon, okay? This is a bit of a formal writing, but if I expand it in epsilon, I see that I get iterated integrations over these differential forms, which are the forms that appear in that matrix, okay? Now, these differential forms are special in this case. They are linear, and so they give rise to what are called multiple polylogarithms, okay? In this particular case, harmonic polylogarithms, but this is only a special case. I don't have time to introduce harmonic polylogarithms and talk about them. You probably know, I mean, you have hopefully all seen classical polylogarithms like Li2, Lien, and so on. So I just want to show you what the result for the, remember, this second integral, J2, is, as someone doesn't know what the Li2, are you laughing about that?
I now know.
You now know.
I met
okay.
enough physicists.
So, well, everybody knows, okay, let's write it. Well, you should tell me, right? You should shout. So let's do the following, right? What is a logarithm? A logarithm is an integral that I can write, for example, like this. One possible way to write a logarithm. A Li2, hoping that I remember the right definition, because there is a minus sign probably, but it should be an integral from 0 to x of dt, the logarithm of 1 minus t over t. Is that correct? Maybe there is a minus sign. Someone of Claude students remembers better than me. I think there is a minus sign. So the Li2 is an iteration of the logarithm integrated again over a logarithmic differential form. And a Lien, in this particular case, is our classical polylogarithms. It's just this thing iterated over and over again, right? So I just integrate again 1 over t over the Lien minus 1. Okay, so start from the logarithm. The logarithm is a bit special. I integrate it from 1 to x if it's log of x, but if it's log of 1 plus log of course, log of 1 minus t is also an integral from 0 to t of du, if you want. U minus 1, right, or something like that. So from here, I can build my classical polylogarithms iteratively. And there is a generalization of this. I can actually change these integration kernels, add in any, if you want, singularities at any points in the complex plane that I like. And this is the space of functions of generalized polylogarithms. But we're only going to need these ones for now, because I just want to say that if you now try to solve this differential equation here, in terms, you can actually solve it in terms of these functions. It's very easy, straightforward to see that you can solve it in terms of these functions if you try. And the result is going to look like this. Of course, in order to get a full solution, and this is something I've not been saying anything about, I need to fix also a boundary condition. Okay? And the information on the boundary condition must come from somewhere else. It cannot come from mathematics. In a sense, it must come from physics or from some information that I know about the integral. Let me write 1 second the result. I don't know if it's illuminating or not, but I want to actually show you one important thing, which is also part of the jargon that we use all the time. So this is what the result looks like. I've now expanded it. I've computed the 0th order in epsilon, and I've also computed the first order in epsilon, right? The first non-trivial order in epsilon here. You see that the first order, so first of all, there are no poles in this case. So close to 2 dimensions, this integral turns out to be finite. This can happen. It has no singularity when epsilon goes to 0. Fine. Second important thing is that you see at order epsilon 0, I get a logarithm, okay? And at the second order in epsilon, what do I get? So I get what we call the Li2, which is an iteration over the logarithm. I'm integrating 2i's over d logs. And then I get products of logarithms, okay? Always two products of logarithms, and the pi squared, okay? Now, what I can do is that I can give to these functions, so pi, I can think about pi as log of -1, okay? So the pi is a logarithm. So if I associate to each integration over a d log, over a differential of a logarithm, so a logarithmic differential form, what I call a transcendental weight, and I call this transcendental weight 1 for every integration. So every time I integrate over a single pole, I generate, if you want, a new non-trivial function because a single pole has a residue. And so the primitive of that integration has to be a function that has a branch cut. It has to have, like, it has to change, right, when I go around the pole. Then I have to give to this function a new name, and I say that every time that I do this integration over a new pole, I increase the transcendental weight. So logarithm of x will have transcendental weight 1, pi will have transcendental weight 1, pi squared will have transcendental weight 2, the Li2 will have transcendental weight 2, and so on and so forth. And so you see that typically we use the letter W. The first, the order epsilon 0 has transcendental weight 1, and that's it, while the order epsilon has transcendental weight 2. Right? And all the terms in the order epsilon have only transcendental weight 2. The Li2 has transcendental weight 2. There are products of logarithms that have transcendental weight 2, and pi squared has transcendental weight 2. Yeah? Sorry, yeah, I'm just saying, I mean, in a sense, if you think about, imagine that you try to generalize this, right? And you say, I'm integrating over something like x minus a. I have some pole in the complex plane. The fact that there is a pole tells me that this is a multi-valued function. The primitive of this thing is a multi-valued function because the integrand has a residue. So when I integrate over it, there is a pole. So when I go around it, I get 2 pi I. So the primitive has to be multi-valued. And so that's kind of a log, right? As we know. This is what we call a logarithm. And now every time I do this again, I add another branch cut in principle, another possible singularity in that sense, and I increase the transcendental weight by 1, right? So if I have something like this, I'm integrating now, let's say that this goes to x, and this goes to t, and this is like u minus a, I don't know. I'm integrating in u, and here I'm integrating in x. I get some function of t at the end of this integration, of course also of b and a, which will have transcendental weight 2, because I've integrated over 2 different single poles. As soon as you have a double pole, then the double pole does not give me a log. When I integrate it, it gives me a rational function, so I don't increase the weight because there is no residue, right? And then if I had a pole, then this function would have transcendental weight 1, right? Even if I integrate it twice. Does this make sense? I'm not computing the residue, it's just that I know that the primitive, because of the existence of that residue, the primitive has to have a branch cut. It has to be a multi-valued function. I don't know, that's how I... It's actually very important because this type of structure is exactly the one that we are going to look at. We are going to look for this structure in the integrand that defines the Feynman integral in order to predict, without doing the integral, what is going to be the analytic structure of the integral when we do it. From here, it's based on the generalization of this. I mean, if someone gives you this integral, without doing it, you will know that this integral is a logarithm because it has a double pole and a single pole. So it can only be a log times some rational function. And this is kind of the type of arguments that we are going to generalize for a general polylog. Sorry, for a general Feynman integral, not for a general polylog. So now let me take this expression 1 second. I just want to copy it to the next page. Because it's nice to have blackboards where you can show more than one formula at once. Here it's a bit more complicated. So this is the result that we got. And now I want to remind you, we had earlier, I think in lecture 2, we had computed the same bubble, but we had computed it close to d equal 4 minus 2 epsilon. Okay, so this was the result close to d equal 2 minus 2 epsilon. Okay, we computed it close to 4 minus 2 epsilon, and let me remind you what this looked like. I mean, I did the computation, I didn't really do it, but from Feynman parameters, I told you, you can do the integral. And we got something like this. We got a pole, in that case, and then there was a 2 and then there was a 1 plus x over 1 minus x logarithm of x plus higher orders. So you see here, first of all, I mean, in one single line, I barely managed to write the 1 over epsilon, which doesn't even exist in the previous one. And the first order in epsilon contains two terms, right? The order epsilon 0 contains two terms. There is a constant, which has weight 0, and there is a logarithm, which has weight 1. On top of that, there is also a rational function here, which I did not have before, right? Before, the rational function was kind of overall, and I removed it. It was a solution of the homogeneous equation. That was the rational function that was overall everything. So if you compare the two expressions, you see immediately why maybe a physicist, maybe a mathematician doesn't care. I don't know what a mathematician thinks comparing the two. You should tell me what you think. But physicists, at least, that were looking at amplitudes and this kind of things already, say, 20 years ago, seeing these two expressions, they kind of immediately thought, okay, the first one is kind of nicer than the second one, because the first one doesn't have this mixing of transcendental weight. It preserves weight. So in the first case, we say that that close to d equal 2 minus 2 epsilon, the bubble is, again, this is jargon, is uniform transcendental, meaning that at every order in epsilon, the transcendental weight is uniform, is not mixed, okay? Which is not true for the second integral, because as you saw, at order epsilon to the 0, you have weight 0 and weight 1. And the second property that is also jargon, unfortunately, is that is that the integral is pure. What does it mean, pure? So this purity means that there are no rational functions, or that if there was a rational or an algebraic function, if you want something that is not transcendental, if something that is not transcendental was overall, and I could remove it in the previous, in the equal to. In the second case, I cannot remove it because it's not overall, it's here. Okay? So why is this nice? Because if a function, so let me say it now very, in a sense, in a pedestrian way, no rational or algebraic factors. What does this mean in practice? Well, it means, what I really mean with purity, it means that if I take a derivative, okay, say in x, of a function that I call pure, and which has weight w, whatever comes out of this derivative will be some rational or algebraic function times a function that is still pure, and it has weight function. Let me not write rational because it could be algebraic, so I don't want to be a little bit more general. But I get a function that is simpler in a sense it is of weight w minus 1. So I decrease the weight by 1, right? It's kind of obvious because if I take this expression here, the one in the first line, and I take a derivative, the first order will become 1 over x. So from weight 1 will become weight 0. And the second order will become a combination, if you want, of this will become a logarithm times some rational function, and these ones will also become logs times some rational functions in this case. And so I will get weight 1 here and weight 0 here in the derivative. This is the concept of purity, which is actually connected, and the generalization of it is, I think, what in mathematics one calls a unipotent function, in the sense that when you take the derivative of something, this something becomes simpler. If it's a system of differential equation, the matrix is kind of nilpotent. Or if I square it enough times, I get 0. Okay, this is a generalization, I think, in mathematics. But for us, in this case, it means exactly that I differentiate it once, and the weight, the transcendental weight, goes down of 1. And of course, it's exactly what I expect, right? Because the form of the equation was this one, right? So at every order in epsilon, I'm doing an integration over 1 d log form, and so I'm increasing the transcendental weight of 1, right? Every time that I integrate over the previous order, I integrate again over a single pole, and so I increase the transcendental weight. Unless something very strange happens with the boundary conditions, the boundary condition gives me some numbers that don't have the right transcendental weight, this is exactly what is going to happen. Does this make any sense? Maybe a little break. I know that for the physicists it makes sense and it's probably boring, but for the ones that have never seen this before, x is for now is a variable. It's just a transformation of variable. I went for the momentum for the p squared to this x in this way, And it was a way to, if you want, you can think about it. I mean, this square root defines an algebraic surface in principle, and I'm kind of rationalizing it because it's a polynomial of degree 2, and so I can practically extend the branch cut and make it again a sphere. That's what I've done. So I've gone to something that it was a square root to the Riemann sphere, and then everything is rational. Very good question. So maybe this we could discuss tomorrow. What do you think? Because this is like part of the explicit solution. So there are different ways to do that. I can just say it in words very briefly. One way to get the boundary condition is you can do the calculation at a given point. Typically, computing the Feynman integral as a function is much more difficult than computing it only at one point. If I choose a point wisely enough, the calculation simplifies, and so I can compute it, for example, at p squared equals 0. In this particular case, for example, this integral here, if I put p squared equals 0, it becomes super simple. It becomes the equivalent of a tadpole, practically. So an integral without momentum, and you can do the integration in 1 second, okay? But this is not the only way how we do this, right? There are other reasons that actually come from physics. For example, physics tell us that the final result has to have some properties. In particular, the final result cannot be logarithmically divergent arbitrarily everywhere, or actually square root divergent, algebraically divergent everywhere. But it can have a divergence, or if you want, discontinuity in general, only at specific points which are dictated by physics. The only specific point where this can happen is p squared equals 4m squared. Okay? And one can actually use this condition to impose that if you want close to p squared equals 4m squared, you get the right behavior. And at other possible singular points, if there were any, there is no singularity. And this is many times is enough to fix the boundary condition. So physics sometimes helps you, so very often helps you also to fix the boundary condition. But I thought maybe this is something that we can do tomorrow. I don't know exactly what we're going to do tomorrow, honestly, but maybe Anna Laura should tell me better, but we will discuss this later. Okay, any other questions about this? Mm-hmm. No, in general, not, because in general, imagine that I have a function which is say log of x plus log of 1 plus x. This is pure of weight 1. If I take the derivative of it, then I get 1 over x plus 1 over 1 plus x, right? And now if these things were multiplying, now in this case, of course, I can put it together and this is one single rational function. But if this was multiplying something else here and here, which is again a transcendental function, then I would get two different rational functions, so it's not pure anymore, typically a derivative. So a derivative typically lowers the transcendental weight, but produces many non-pure terms that then you have to somehow rearrange later if you want. Well, the uniform transcendental, if I have something, say that, I mean, this is also honestly, it would be interesting to have Johannes here, because this is something that people call this uniform transcendentality and pureness. Some people consider them as two different properties. Some other people consider them one as a sub-property of the other one, okay? So the way I think about it, I try to differentiate it, okay? So for me, if something is UT, uniform transcendental, it just means that it has the same weight. So it could be non-pure. So for example, I could have 1 over x times log of 1 plus x, and then I could have plus 1 over 1 minus x times log of x. I mean, this thing has uniform weight, but it's not pure, okay? It only becomes pure once the prefactors are the same and I can remove them, right? So if you want, there is no prefactor, no rational prefactor. So some people say, okay, the function is pure if it is UT and it has also one single rational prefactor. But I think in principle, the purity condition is actually something, since it's really connected to the unipotence position, unipotence property, I think is a bit more general. This is my understanding at least, because I could have something like, I don't know, a Lie2 of x plus, I don't know, some coefficient at some log of x. This is not UT, as long as the C is a number, right? This is not UT, but it is pure in the sense that if I differentiate it, the weight goes down, right? The maximum weight is 2, 2 and 1, and it goes down to 1 and 0. So I think this is a little bit, is one of the things that people in the community call differently. I think maybe it's very common to say that when people talk about purity, they also would like this thing to be a log squared as well. So that really, it's also UT and pure. But I don't know. I mean, I've heard both. So this is unfortunately, yeah, what I was saying in the first lecture, that physicists don't really agree on definitions 100%. Mm-hmm. Mm-hmm. This is matter of debate. So I think that in principle, in principle, this is one of the things on which, for example, physicists don't agree with Francis Brown. I don't say mathematicians, because you said that if we say mathematicians. For example, when we work with polylogarithms defined on elliptic curves, or these kind of things, how do we assign weight there? So what we would like to do, because for us, weight has a very strong physics implication. So for example, when we compute a scattering amplitude, there are some conjectures that have never been seen violated, okay, but these are conjectures that tell you that the maximum weight that you can encounter in a scattering amplitude is fixed by 2 times the number of loops. Okay? So if I do a calculation at 1 loop, I will get weight 2. In 4 dimensions, at 2 loops, I will get weight 4, and so on and so forth. You can kind of argue around this, why this should be the case. There are many good arguments, but I don't think there is a mathematical proof for this. In particular, in super... Exactly. So now what happens? So in all the polylogarithmic cases, this conjecture is always verified, right? And so one could maybe try to prove it, and I think there are some arguments. Now, what happens when you go beyond that? When you go beyond that, you could require, and I think this is the most natural thing for physicists, that when you go to a more generalized surface, there are still these special points, like singular points, or maybe on a general surface, say a MAM point, where the surface degenerates to something simpler, and even if you had, like, say, complicated periods of Calabi-Yau or I don't know what, everything degenerates to logarithms there. And now in these special points locally, I can define weight in the same way, because I only have logs. So locally, I know that from physics, I know, as we discussed, right, that at the end of the day, I will have these divergences, these branch cuts, which are either algebraic or logarithmic. There is nothing else at all the singular points. So if I go at a special singular point, I can see these logarithms. And then the hope, I think what physicists kind of agree on, is that this will be the natural generalization. So define the weight locally at a singular point in terms of logarithmic integrations, because at that point you go back to logs. But this is not completely consistent, as far as I can understand, with what, for example, Francis Brown would like to do. I think to anything that has logarithmic singular. So take a differential equation with rational coefficients, linear systems of differential equations with rational coefficients, which have regular singular points. These ones you can apply Frobenius method, right? And so you know the solution at close to every singular point will be holomorphic solutions in series and then logarithmic towers, right? And if the point is special, as Christoph taught me, is one of these MAM points, I don't know, then you get all the logs, right? All the tower of logs. If the point is not a MAM point, then you might miss some of the logs. You might get more holomorphic solutions and I don't know what. But if you go close to one of these special points, then definitely you have the full tower of logs. And so you can really count the transcendentality in this sense close to that point. Exactly. This is the thing that we kind of, I don't know, Christoph, do you agree with my explanation? I don't know. Yeah, I don't know. This is what we, but I crazy symbols. No. But this is okay. But this is what. Okay, but look, as I said, as I told you, right, in the community. So this is for us. This is a very hot research topic, right, for a small part of the community, people working on Feynman integrals. So, and there is also a continuous discussion, as I said, with mathematicians, where somehow this kind of definition would not apply, right? Because, say, I think Francis Brown, if I remember correctly, likes to say that elliptic integrals have transcendental weight 1/2, because they go a square root of pi. And this would not work, right? Because our integrals have either weight 1 or 0, right? Weight 1/2 doesn't exist. Either you have the log or you don't, when you go close to a singular point. It's local, yeah. Yeah, that's what we do. Yeah. And I think this seems to be natural, because when you have your amplitudes and you go to the singular points, I mean, the singular points correspond also to singular kinematical points. So maybe you have a general amplitude, but then your kinematics degenerate, or maybe a mass goes to 0 or something like that. and then your elliptic curve becomes a sphere, and then from elliptic polylogs you go down to polylogs. But now in this limit, you would like to see that the amplitude has the right transcendental weight, because it's right, and then this definition works somehow in that limit, right? Sorry. Of course, yeah. Yeah, yeah. Yes, but you have to be, so that's the problem, right? So say, it depends, I think, on the algebraic surface or on the geometry that you're working on. I think if you are working on the simplest generalization that we ever encountered of polylogs, which is elliptic curves, then I think there is a theorem, again, Christopher, say something wrong, you tell me, that every regular singular point of this differential equation is also a man point. And so at every one of these points, is a maximum unipotent monodromy point. It means that you find all these logs, right? So you find practically the holomorphic solution and the one with a log. Okay. If you go to, but I think if you're in a more general surface, then you might get singular points where you don't find all the logs. And these singular points, and at those points, we don't know how to define this, I think, uniquely. Am I saying? Then. Well, but you have to adapt your definition a little bit. I mean, I don't know if we will. So practically what you do is that you, what determines if you want these logarithmic singularities are the solutions of the homogeneous equations, which will become periods of these geometries, and you have to redefine the period. So if you want the period that is holomorphic at one point, will not be holomorphic at the other point. So I have to use two different periods. But if I use two different periods, yeah, this definition is consistent, as long as I use the right period in the 2 points, though, right? So I have, like, of course, yeah. Well, but. Yeah, but. It would be, yeah, exactly. So I think we were kind of trying to say this. So you somehow really have to redefine. So it's not going to be exactly the same integral that has the right weight everywhere, only locally, right? Otherwise, it's a linear combination of those integrals. Good. So now I just wanted to say maybe one brief thing. So what happens, now we have seen what the solution looks like. And I wanted to just say what happens if I do the same thing for close to 4 dimensions, right? So someone asked me yesterday, could I have done the same thing close to 4 dimensions? So I derived the differential equations, which we actually wrote for general D. And then the only thing that I did close to 2 dimensions was actually integrating out the homogeneous solution. And then I got something epsilon factorized, which is very nice properties. Now, if you try to do the same thing close to 4 dimensions, I mean, you have, again, your bubble, right? You can compute the cut, which corresponds to the homogeneous solution. And this is some constant, again, and the root that solves the homogeneous solution looks a little bit different. If you remember, I mean, in D equal 2 was, in D equal 2 was 1 over square root. Okay, so it looks a little bit different, but it's still an algebraic function close to D equal 4. And I could try to remove this, right, and try to rotate it away, and then ask myself, what do the equations look like close to 4 dimensions? If I do this little exercise, then I get, in the same variable x, I get the following equations. J1, J2. I get an epsilon factorized part, which looks like this, hoping again that I've done everything properly. And then I get a part that is not fully epsilon factorized. Okay, so I see 2 problems, right? So you see, when I do this rotation, since I've only looked, if you want, I've only solved the homogeneous part of the equation for the bubble. Of course, there is no reason that the coupling of the bubble to the tadpole, which is this entry here, should be fixed, right, by this rotation. It doesn't, in fact, it remains there, right, in this general case. And also, so I see two problems. This is one problem. This is problem one. And the problem two is this one, because in the epsilon part, I get something which has now a double pole. This is not the differential of a logarithm, right? So it has a singularity, which is of degree 2. And so that differential form, when I integrate over it, does not increase the transcendental weight of 1. It means that clearly solving this, I mean, I can solve this equation. It's very easy to solve, right? I mean, it's practically in block diagonal form. So I have order by order in epsilon, I just solve the equations. But I'm going to get that messy solution that I saw before. So there will be rational functions coming from the double poles. There will be mixtures of weights coming from the fact that there is a double pole and there is a single pole and so on. And so kind of the question is that we are trying to ask now in the very little time that I'm left, but they were good questions. So I'm actually happy that we discussed about this. Could have I predicted this right from the beginning? Instead of doing the calculation, checking and try to do this rotation and then I find now a bad result, could I have predicted that the result would have been bad from the beginning? Okay, and indeed, the prediction is actually super simple, okay, and might be even be too straightforward if you think about it. So let's go back to, so we need to actually look at our integrand in some parameterization. In principle, we can do this in any parameterization. We could do this even in the loop momentum parameterization. It's just a bit more difficult, and I mean, I don't know how to do it, but people like Johannes, for example, knows how to do this also in loop momentum parameterization. So 95% of the people, as far as I know, do this in parametric representations, in some specific parametric representations, say in Feynman parameters or in Bykov, or in specific 4-dimensional parameterization where you parameterize your loop momentum really in 4 dimensions. So let's use Bykov, which is maybe not the best in some cases, but is very convenient. And it's also because I already written this result. And I want to go back to the bubble with arbitrary powers of propagators and in arbitrary number of dimensions. And the parameterization looked like this. This we wrote it in lecture 2, I think, or maybe yesterday. Bit too small. Squared divided by 4 to the d minus 3. I hope you can read it. I mean, it's not so too important. There is a d minus 3 up there. Sorry, let me try to. No, I'm going back. I just wanted to fix it. Sorry, I just wanted to fix it. Okay, so this was the general parameterization in general number of dimensions. Now, I would like to actually have a look at what the integrand, without really solving the integral, okay? I would like to have a look at what the integrand looks like close to 2 dimensions for specific values of alpha 1 and alpha 2, okay? So in particular, let's take the simplest case, which is alpha 1 equal alpha 2 equal 1, which is also the master integral that we computed in 2 dimensions. And let's take d equal 2 minus 2 epsilon, okay? Now, modulo some prefactor, again, which I don't really care about, I can, a numerical prefactor, I can write this as the integral over z1, z2, divided by z1, z2. Then I have, as you see, a square root of that polynomial, p squared, z1 plus m squared, minus z2 minus z1 minus p squared, squared over 4. And then I have something else. Okay, and this something else is raised to the power epsilon because it's going to be 0 when d is equal to 2, right? So I've extracted everything that is not 0, 1. So I've extracted out everything that is non-1 when d is equal to 2, and then there is some corrections here, right? Everything else. Now, these corrections, I'm going to forget about them, okay? One of the reasons why you can think about why I want to forget about these corrections, which in order to do this consistently, though, I have to be consistent. So this one has to have also the right properties. But one reason why I can forget about them is because when I expand it, I get 1 plus epsilon log plus epsilon squared log squared plus epsilon cube log cube. So I get naturally logarithms, dilogs from there. So that part here, if this integrand is in the right form, then this will here will not contribute anything that are not logarithms, like the ones that I already know that are actually the d logs that I want to find at the end. So I'm going to forget about that. It's going to practically at every order in epsilon is going to be a pure function that increases transcendental weight at every order in epsilon, right? 1 plus epsilon log log plus epsilon squared log squared plus epsilon cube log cube and so on. Now, what can we say about the rest? The rest is actually very simple, right? It's a double integral in two variables. And now what we are going to do is that we are going to look iteratively at the structure of this this algebraic function in the complex plane, okay? Now, I understood that some of you are not super comfortable with this, but I hope that, I'm really not doing anything too complicated in some sense, I hope at least. But please tell me if I say something strange, okay? So let me try to write this like this. So let me write this as an integral first over z2, iteratively, and then I have an integral over z1, over 1 over z1, and then I have some polynomial of degree 2 in z1, and in principle z2, and the mass, and p squared. Okay? That's what this structure is, right? I have a polynomial there, and I have a pole in z1. Now, let's focus on this part for a second, okay? And let's imagine, so let's look at the integrand, not at the integral, on the complex plane, right? So I have a complex plane of z1, so this is the real part of z1, this is the imaginary part of z1. Now I can ask myself, okay, what is the analytic structure of this function, that is the integrand? Well, the integrand definitely has a pole here at z1 equals 0. And then it has a branch cut somewhere. It will have a branch cut because there is a square root of a polynomial of degree 2, which has two solutions, right? It's a polynomial with two solutions. So let me assume that I can choose, say, z2 and the mass and p squared, such that the two roots are ordered here on the real axis. They don't have to be on the real axis, but I have to draw them somewhere, right? So let's assume that the roots, which will be function of z2, m squared and p squared, I can choose them somewhere there. These are my two branching points, or what we call the branching points. What it means is that on the left and on the right, if you want on the real axis, the argument of the square root is positive. In between, the argument of the square root becomes negative, so there is a branch cut here, okay? There is a discontinuity in the integrand, not in the integral, but in the integrand. Now, the conjecture, if you want, I can call it conjecture, but maybe it's more obvious than a conjecture, is that the analytic structure of the integrand determines completely the analytic structure of the integral. I mean, I don't think it's a conjecture, but it's kind of obvious, right? But this is what we do. So we just look at this and we say, okay, I mean, now what can I say about this integrand? There is this pole and there is this branch cut. So there are two different, so if I think about this from the point of view of homology and cohomology, right? I have a set of differential forms and I have a set of possible contours. This is my differential form. And there has to be a set of independent contours associated to this differential form. The only two contours that I can have are this one and this one. And these two contours are clearly not independent because of the global residue theorem. So if I take like a big contour around here and I send it to infinity, I get 0. So the sum of these two contours is equal to 0. So the sum of these two integrals is equal to 0, so they are not independent. In fact, there is one differential form, which is a d-log, okay? And there is one contour, which corresponds to the contour that goes around to one of the two singularities. The easier one is clearly this one here, okay? So the cohomology, if you want, associated to this thing is very simple. There is one differential form, there is one singularity, if you want, that is z1 equals 0. So this thing is a logarithm. It's nothing, just without doing the integral, right? I know that this integral, if I do it, will give me a logarithm. The primitive of this function will give me a logarithm. It also tells me something else. It tells me that it will give me a logarithm, and the rational function or algebraic function in front of the logarithm will be the residue at that pole, right? So is this something obvious that I'm saying, or is this something very strange? So that if I go to the next page, right, let me maybe copy this to the next page. Oops. What's happening? Very nice. Why did it do this? If I go to the next page, what this analysis, so without doing the integral, just this analysis is telling me that if I do the integral in Z1, okay, I'm going to get some prefactor, let's call it A, times a logarithm of something. I don't care about this something, because this is a log. I care about this prefactor. This prefactor is the residue at the pole of the integrand. Does this make sense or not? You think about how you construct a logarithm, right? I mean, you have, I don't know, the x minus a, this is log of x minus a. The residue is 1 here, and in fact, is also the constant in front that you get there, right? If you imagine to get something a little bit more complicated, right? Which is, then I have actually two different poles, right? And these two different poles will also, there will also be two singularities. There will be the global residue theorem. There will be a logarithm of a bit of a more complicated thing, but the residue in front of this logarithm, sorry, I call it residue, of course, but the coefficient in front of the logarithm that I will get will be the residue, say, at x equal a of the remaining function, right? X equal b of the other one, which is b minus a or a minus b. Right? So I will get the log from that one. I will get something a little bit more complicated. I don't know what that is, but then I will get a minus b in front. Right? So I don't need to do the integral to know that this is a minus b. That's what I'm trying to say, right? Because it's just the residue, and this is the only information that I need. I just need this residue. So because this analysis is telling me, do you have a question? No. Okay, I don't know. But Bernd, am I saying something wrong? No. Yeah, partial fraction, of course. Partial fraction, yeah. I mean, it's just, I wanted to just justify that, but this thing works also with square roots, where partial fractioning is a bit more complicated, I think. But, okay, so very good. So then we can do this, right? And we know that this integral will be what? Will be an integral over Z2 divided by Z2. Then there will be the residue of this, so it will be this square root evaluated at Z1 equals 0, right? We can have a look at what the residue was, what the square root was. It was this one here. You put Z1 equals 0, so this one goes away and this one goes away, right? And so you get another square root, which only depends on Z2, and is again a quadratic polynomial in Z2, right? It's a polynomial of degree 2. So again, I don't care what it really looks like for this analysis, but I know that I will get this, and then I will get a square root of a new polynomial of degree 2, now in Z2, in p squared and m squared. And then whatever was in front of this was a log of some type. I don't care about, okay? Now, why do I not care about this? Because this is telling me that through this first step, whatever integral I get out of this will have, again, uniformly increase the transcendental weight of 1, right? And now again, I don't care really about, I mean, I don't need to be able to do this integral. This integral will be complicated. We'll give a complicated Lie2, I don't know, or maybe some other complicated function, I don't know. But the only other question that I have is this integration, will it again purely and uniformly increase the transcendental weight or not? This is the only question I have. And again, I mean, this is the same situation as before, right? Because also in Z2, I have a pole, and I have a square root of degree 2. There are again two branch cuts. There is again exactly the same situation as before. So I have these two different contours. So again, I know that this second integral, if I forget about this log for a second, will act exactly like a logarithmic differential form. We'll add one more singularity to the game. If you want one more independent integration contour in the sense of the homology, right, of the surface associated to this, which is another contour around another pole. And so I know that this will give me, in turn, another prefactor times, if you want, an integral over some d log. I don't care what it is. And the other one was also an integral of a d log because it gave me a log, okay? And so the final structure of the integral is going to be this one. And this a, I can predict it again. Let's go back to the root. Sorry, where was the root? Here. I know that I have to also put Z2 equals 0, right? Because it was the second pole at Z2 equals 0. So you see we get square root of p squared m squared minus p to the power 4 divided by 4, right? If I read correctly from here. So this is going to be our residue. Let's copy it. So the final result is going to be 1 over this. And then there will be some integrations over some d logs. I don't know what they are, and I don't care. Okay? So now out of this, I mean, you see, well, from here you immediately actually recognize something, right? Because if I write it a little bit better, okay, there is a factor of 2 that I can pull out, and then I have a p squared, and then I have a 4m squared minus p squared. Now modulo up to a sign, this is exactly the solution of the homogeneous equation in d equal 2. Right, in d equal 2, we knew that this was the solution of the homogeneous equation. In fact, by taking these iterated residues one after the other, what have we done? Remember, how did I define a cut on a Feynman integral? I defined the cut, modifying the integration contour so that I go around all the singularities of the propagators. What I've done here is that even if I didn't look at the propagators, I've just taken a different representation, and I've actually picked up all my possible residues, so I've deformed my integration contour, and at the end of the day, I got the maximal cut. Okay, but the maximal cut is now a prefactor in front of something. I mean, the analysis is more general, right? So I have also the integral over d log. So this is a general information on the full integral. I know that the full integral will be this one algebraic function in front of a string of d logs. So this is a definition of a pure integral. It's uniform weight. It has only d logs, and this epsilon part, as we said, that every order in epsilon, it adds uniformly another log, so another transcendental weight. And it has one single rational prefactor, algebraic prefactor, sorry, in front. Rational if I use the variable x, which is overall and is equal for everything. Which means if I multiply it out, which is exactly what we did when we solved the homogeneous equation, right? I get something that is a pure NUT integral, right? Which is what I wanted to get from the beginning. So this analysis practically tells me, demonstrates, proves conjecturally, okay, because I don't think this is a proof. I don't know if how mathematicians react to this. I think this is typically, we call it a conjecture in a sense that we conjecture that all the integrals that are in this form, if you find them, will satisfy equations in the form before. So which will be epsilon factorized, and the entries in the matrix will be in d-log form, okay, because there are only d-logs, and there is this prefactor which I have to remove. Okay, I have to remove the prefactor. Is there any question about this? Does this make any sense? Yeah? Mm-hmm. This should give you the at this point. Yeah. So once you're talking now about the first integration, right? So the first one here, yeah. You mean in the second integration? Yeah, because I don't want to really do the integration. I'm not trying to perform the integration here. Right? I'm trying just to make a statement about what is going to be the analytic form. So what is going to be the property, what are going to be the properties of the function that comes out of this integration, if I were able to do the integration. So is the function going to be of uniform weight? This is my first question. And is it going to be only an iterated integration over logarithmic forms? And what I'm trying to prove is that whatever I do, I know that at every step, I will get another logarithmic integration to do. Of course, this logarithmic integration, I will not get just a log, right? Because there will be this logarithmic integration over something more complicated. So I will get typically what is called a multiple polylog, or generalization thereof. But the important thing is that at every step, the integration is logarithmic. And this is the only information that I want to carry with me. Because then when I solve the integral, I solve it from the differential equation. So this just tells me that this is a good integral. So it means that this integral here, I can take it and I can derive differential equations for it. And the differential equations for it will look very nice and will allow me to solve it in terms of the functions that I want to. And it will be typically simpler to solve it with differential equations than to attempt to compute this integral for real. But really, in practice, this is what I do, right? So I look at the analytic structure, And then I pick up, if you want, I see what are the independent contours, because the independent contours tell me what kind of function is in front of me. As you would say, what function entered from the door, right? And then I can look at it, and then this thing will tell me, in this case, this is a logarithm, because there are only two branch cuts, there is only one contour, there is one differential form. This is a puncture on a Riemann sphere, somehow. It's a log, it's a d-log, so I can just keep it as it is and go on, right? If this was more complicated, we can make an example, but how much time do I have still 15 minutes? Yeah. So we can make maybe a more complicated example now in a second. If the thing becomes a little bit more complicated, then I might not get just a simple structure. So for example, this root might become a root of a polynomial of degree 4. If this is a root of a polynomial of degree 4, then I get an elliptic curve. I get two different branch cuts. Maybe there is also a pole, whatever. And so I have more independent contours. And so these more independent contours tell me that there is not only a log, but there is something more complicated there, right? And then I have to decide what to do with that. Is this good or is this bad? Is this the right generalization of a d-log or not? Yeah, that's okay. Okay. Now, okay. I don't know what is more interesting, because I could briefly say what happens in the elliptic case. We could also discuss this tomorrow, since I learned that problem session in mathematics means open problems. So actually I can discuss it. It's not, this is what Bernd told me, that problem session means open problems, discussion of open problems. So, no, we can do whatever we want. I want to say just maybe briefly one thing. What would have changed if I did the same analysis in 4 dimensions? I mean, could have I said in 4 dimensions that this integral was not good? Because of course now we have said that it's good in 2 dimensions, but what happens in 4 dimensions? Well, now in 4 dimensions it's a little bit tricky, but let's maybe copy this. Yeah. And so what happens if I fix d equal 4? Didn't, but maybe it's here. I didn't even write it for you. We can practically do it by hand, because you see immediately what happens here, right? So you have, if I put d equal 4, you get some prefactor. Again, then we get the same contour. I'm going to put like also alpha 1 and alpha 2 equal to 1. But now the square root is at the numerator. Now, from the fact that the square root is at the numerator, well, it's kind of immediately obvious what goes wrong from the integrand, right? Because since the square root is at the numerator, it means if you want, I can also write it as integral over gamma, dz1, let's write dz2 over z2, and then dz1 over z1, like before. Then I have my square root at the denominator, if I put it down, z1, z2, the same one as before. And then I have a polynomial now here at the numerator. Right? And so you see that kind of the analytic structure is the same, in the sense that the singularity, there is always this pole and this branch cut. But so somehow the analytic structure still tells me that this is a logarithm of some type. But the numerator tells me that in Z1, I actually can get double poles at infinity. I can get poles in the complex. So some pieces of this, right? For example, this term here will cancel this Z1. And so I will move, okay, the pole from 0 to infinity, but it's still a single pole. It's not so bad. But this one is bad, because this one here, Z1 appears squared. So this actually gives me an integral of the type integral in dz1. There is a square root at the denominator, and there is a z1 at the numerator. This thing, if you look at it, if you do a projective mapping, I don't know, you send infinity to 0, you will see that this integral here has a double pole at 0. It goes like this, Right? So there is a part, you see, this integrand immediately tells you I'm as bad as I could be, right? Because a part of me is good, is logarithmic, it has a pole at 0. Another part is also logarithmic, and it has a pole at infinity, so it will have a different residue in general. So it could be non-pure, this first integration, but okay, this is not necessarily a problem. One has to see what happens next. Then there is also a part which has even a double pole. So that part with a double pole, when I integrate it, it does not give me a log, but it gives me an algebraic function. So I practically get, after the first integration, something of weight 0 and something of weight 1. That then has to be integrated again at the second step, and so unless something magical happens with the integration contour and maybe something cancels, this integral is not going to be good in general. Okay? So from here, I could say that this is maybe not a necessary, but is a sufficient condition, if you want, because it could still be that some magic happens and the integral looks bad, but it's still going to be a good integral at the end, but some sort of conspiracy has to happen. Otherwise, this integral is a bad integral. Okay. Then now I wanted maybe to briefly say something about what happens in a more general case. Since I don't have a lot of time, let me try to be brief and take an example, which is the one that we also discussed millions of times, which is actually a generalization of the one-loop bubble to two loops. This is now some sort of a two-loop bubble, where I'm assuming now that the two propagators here have a mass, and this propagator here has a different mass. Okay? This is interesting because whether this mass is 0 or not, you get something polylogarithmic or something elliptic. Okay? So what does this thing look like? So I'm going to now simplify my life a little bit, because otherwise the formulas become too large. Okay? And I cannot write them on here. But in general, if I go to Bykov, I need 5 different variables, if you remember, because there are 5 different scalar products here. So I will have 5 variables. I will have the 3 propagators, Z2 and Z3, and I will have a polynomial, okay, B of the Z's and of S and of the masses to some power. Okay? This will be my Bykov polynomial, is the gram of all the momenta, as we discussed. This is what it looks like. Now, this polynomial will have a bunch of singularities, and we could go, say, close to d equal 2 and analyze all these singularities. So all these 5 integrations, one after the other. Okay, we could do this. This is a bit of a long exercise, and it requires a lot of writing, but it's possible. So what I'm going to do, I'm going to look just at a subset of these singularities. So I'm going to actually freeze some of them, say, in Z1, Z2, and Z3, instead of looking at all the singularities in them, I just pick only those residues at Z1, at Z2, and at Z3 equals 0. This is what we call the maximal cut. Now, in this case, the maximal cut is non-trivial because it is a two-loop integral. So the maximal cut doesn't give me a function integrated already, like an algebraic function, but it gives me still an integral. I still have Z4 and Z5 to do. I still have 2 integrations to do. So let's actually do this. And this will actually give us some information on the integral, but only for what concerns the homogeneous part of the differential equation as it satisfies, because the maximal cut, as we said, practically restricts our perspective not on the full system of the, not on the full equation system, but only on the homogeneous part. So it's a little price to pay if we want to simplify our life a bit, okay? It's not really necessary, but it could be done also better in a different way, but I don't want to introduce 3 million different parameterizations, so it doesn't really matter. At the end, we are left, if I cut everything, we are left with an integral in the last 2 variables, Z4 and Z5, divided by polynomial here. So it actually turns out to look like this. The polynomial of degree 2 in Z4 and Z5. So I'm going to actually write it like this, making explicit the 2 roots in Z4. Okay. Polynomial, it doesn't appear in a square root in this case. So if you put d equal 2 up here, actually I think the coefficient up here is, sorry, the coefficient that I didn't write here is d minus 4 over 2. okay? So if you put d equal 2, then you get actually this denominator, or minus t minus 4 over 2. You get this denominator that we have there, right? So there is no square root at this point, but it's still a polynomial of degree 2. Polynomial of degree 2 in Z4 and Z5, so I can write it like that, okay? With the two roots, which are whatever, they're going to be half p squared plus Z5 plus minus, there is a square root of something, it's kind of ugly. This delta is another polynomial itself. Okay, I don't know if you can read what I wrote, but practically what do you see from here, right, is that at this point, in these two last variables, so for what concerns, if you want the max cut or the homogeneous part of the integral, what I get is the first two integrations are clearly in Z4, they're clearly as logarithmic as before, right? This is actually even simpler, there is no square root. So exactly as before, I know that in Z4 I have two poles, they are not independent, I can pick one of the two, and the residue, so I will get a d log, and the residue will be a plus minus a minus, right? Partial fractioning, as you were saying before, right? So I will get a plus minus a minus, and what is a plus minus a minus? Well, if you look at the roots, it's exactly the square root of delta. It's proportional to the square root of delta. So what I get when I pick up, when I do, if you want the first integration, let's go to the next page, is that the integral becomes, I'm left with an integral in Z5 of this big square root that I wrote before. And then I know that the rest was an integral over some logarithm. An integral over some d log that gave me a logarithm, okay? So this is what I'm left with. And here you see the new thing happening, right? The first integration worked in the same way. The second integration becomes more complicated because somehow I produced this polynomial of degree 4 out of the roots, if you want, of the original polynomial, of the Bykov polynomial. And so if I do the same analysis as before, now the things are a little bit more complicated, right? Because in Z5, this is the imaginary part, I have now 4 branching points, which I can conveniently order on the real axis, but it doesn't have to be the case. But I have, of course, 4 different roots, which will depend on the values of p squared and m squared. I forgot square, yes. Let me see here. Thank you. Yeah, I forgot square. I mean, even if you add being cubic in Z5 would have been also elliptic, right? But in this case, it really comes out quartic. In this way here. So I have 4 roots. 2 of them are, of course, coming from the same polynomial in between, and the other 2 are there. It doesn't really matter what they are, because again, we are not trying to solve the integral, right? We are just trying to say, what is this integral going to be? And from here, of course, the situation becomes a little bit trickier, right? Because if I order the roots naturally like that, then this is a possible way, if you want to put my branch cut. So from the, again, from this big circle at infinity, I can say that this one is one of the integration contours. I can call it C1. And then if you want, the other integration contour would be the second cycle that corresponds to integrating between the other 2 roots, right? And these 2 are independent now. There is really 2 of them, and they're really independent. So somehow homology 2 contours, there have to be also 2 independent differential functions. Well, do you see that or not? Yeah. The elliptic curve, you see it, of course, from the root. I mean, if I call this one, if I call this one P4, is a polynomial of degree 4 in Z5, then I have y equals, or if you want, y squared equal P4 of Z5. Right? This is my elliptic curve. And of course, from the point of view of the integrand, I see just the, if you want, the branch cut structure, right, of the integrand, which tells me whether I know or not that it's an elliptic curve. I mean, if I'm naive, I'm a physicist, I don't know elliptic curves, right? Because I'm not a mathematician. I could still say, I know complex analysis, right? So I know complex analysis, so complex analysis tells me that there are two contours here. I also know, if you want from homology and cohomology, there have to be two differential forms. There is a second order differential equation here, right? And this is, if you want, the starting point. Now, I mean, I think it makes sense to stop here. Maybe we can go a little bit more in detail tomorrow if you want. But it's a starting point to generalize the analysis that we did for the polylogarithmic case beyond polylogarithms. Because you see, I will encounter these objects, and then I have to ask myself which ones are good, which ones are bad, and what does it mean being good and being bad? What do I want from these integrals, right? This is somehow kind of matter of debate, right? It could be an open problem. With Christoph and other people, Sarah, Sven, there are many people that have been working on this, Claude and Stefan Weinzel and so on and so forth. There are many people that have been thinking about how to generalize the analysis that we did before, trying to use information from mathematics. What do we know about these surfaces, these curves? And from what we know from the curves, what can we expect that the integrals can look like at the end, such that they have the right properties, as I was saying before, right? That maybe when I go to singular points, these integrals have the right transcendental weight in the sense that I define it with polylogs, for example. A form like this one, we typically like it because this is a form of the first kind on the elliptic curve. It doesn't have any extra singularity. So somehow it acts itself as the residue of the integral. Typically what we would say is that this thing here is really the residue of the integral. So the integral is elliptic. In a sense, it's kind of a d-log integral, which has at the end this residue. What does it mean, this residue? It means that if, depending on which contour I choose, the first period, which is omega 0, I mean, I can have two periods, omega 0 and omega 1 on the curve. One of them is holomorphic, the other one is not holomorphic. The holomorphic one corresponds to having done this integral around the particular contour, the holomorphic contour. This one will be somehow the generalization of the square root that I had before. This is how we try to think about this, right? Before I had the square root, which was the coming out of the last integration, while now out of this last integration, I have something that is that, right? And I cannot do anything here. There is no residue to pick. There is no singularity. There is nothing. It has no residue itself, so it is my leading singularity, or the final residue. That's also why it's what is called the leading singularity. Johannes yesterday explained or tried to say that people also refer sometimes to maximal cut, leading singularity, and so on and so forth. In this sense, you really see why it's nice to call this final object that pops out at the end of the integral the leading singularity, because I'm really looking at all the singular points, I'm picking up all these residues, and at the end I'm left with something, and I call this thing the leading singularity. This is my understanding, somehow, where this name comes from, but I don't know if there is a better way to. Okay. But of course, on an elliptic curve, there are more complicated things, because you will know that on elliptic curves, there are these forms, which are forms of the first kind, but there are also forms of the second kind, which have double poles. The forms of the second kinds of double poles, they are not logarithmic. And so the question, in a sense, what happens with those ones? This is the tricky thing, right, in Feynman integrals. Where do they go? And how do they give us integrals that still have the right transcendental weight? Okay. We have our own way to understand this, but I don't have time to explain it in 1 minute. Maybe we can talk about this tomorrow if you want, or I don't know. Does it make sense to stop here? At least I managed to, I think, introduce what is known, I think, and this is what is topic of research today, in a sense. I mean, people have been writing papers on this past 5 years, something like that. Thank you.